Welcome back. In this video lecture, we are going to look at overlapping double layer interaction. Okay. We are going to consider if two charged surface interact with each other. Okay. How they will interact, right? So let's say we have looked at the the electrical double layer models. Uh, say right from Helmholtz model, Guy-Chapman and Guy-Chapman-Stern model. Okay. Now, let's say if we have two charged surfaces, right? Uh, so when they interact with each other, there can be electrostatic repulsion, right? Due to overlapping of double layer, right, between the charged surfaces. We are going to look at these interaction in this video. Let's begin. Yeah. So in this schematic, we have shown the overlapping double layer. Okay, and I have mentioned interparticle repulsion, but it can be interparticle. Also, it can be repulsion between two objects, any given objects. Okay, right. So, so imagine you have the charged surface. Let's say you have one charged surface, right, which is negatively charged. Okay, and you have another charged surface or the similar charged surface, right, and both will develop the electrical double layer, right, because of the diffuse. It can be due to diffuse counterions or strongly bound counterions or weakly bound counterions, but there will be electrical double layer between these two objects. What if these two objects, when they approach very close with each other, there will be overlap, right, between the double layer. Okay, and when they overlap, there will be repulsion between the two. That is because of the overlapping double layer, okay, of each object, right. Right. So that is exactly what we are looking at in this lecture. Okay. Right. So we are going to develop an equation that is going to be uh, you know electrostatic repulsion, right. What if let's say we have electrostatic repulsion, right, how they will be varying as a function of the separation distance, right. That is exactly what we are going to look at now, right. Our starting point is going to be this equation, that is we are going to say at equilibrium or when they are at a stationary, the force due to electric field and pressure force both will be equal, okay, but both will be counteracting forces, right. So one will be both will be acting in the opposite direction, right. So but at equilibrium we can say that the force due to electric field and force due to the pressure are going to be the same. So this is our starting point, but this can also be expressed as the derivative of pressure with respect to x, or the derivative of psi, that is the potential with respect to x multiplied by the charge density. So this can also be expressed by equation 2. Alternatively, you can also obtain this equation using the Navier-Stokes equation for a special case. So for special case, we can also include the external force, other external force like electric field, although we have ignored magnetic field in this case, right, for brevity. So you can consider both the external force, that is the gravitational as well as electric field force, as we have mentioned here, right. And using this Navier-Stokes equation, because we are talking about the case where the equilibrium is attained, or both this plate are kept at a distance where they are stationary. So you can say that there is no fluid flow. So any term associated with u, velocity, can be neglected. Okay, and if you say that the body force, that is the gravitational force, compared to the force due to electric field, if If it is far lesser than the force due to electric field, we can also ignore the gravitational force for this problem. Okay, then one would get the equation, that is the minus del P equal to minus rho star del psi. Again, further we want to simplify this problem by assuming that it is a one dimensional problem, which means that the variation of potential in y direction and z direction are ignored. At the same time, variation of pressure in y and z direction are not considered. So, by simplifying in this way, you can get the equation that is given in the equation number 2, that is this one, dp by dx equal to minus rho star d psi by dx. Okay, so this is going to be our governing equation for this problem. So what is this pressure? So the pressure here that we mentioned is the osmotic pressure. So when they overlap with each other, so when this double layer overlap, what will happen is they actually prevent the flow of ions into this domain, right? Because when they overlap with each other, it actually prevent the flow of any ions within this domain, which means that they are making this volume, this space, right, inaccessible to ions, counter ions, which so such that they will not be able to freely move around. For example, any counter ions here cannot move, okay, within this domain. So that will cause some sort of imbalance, right, osmotic imbalance. Okay, so what they will do, they will try to access more area by compressing this the object, right, towards each other. In that way, the ions will get more accessible volume. Okay, so this is called osmotic pressure, right, due to imbalance, right. So this pressure is acting in the uh, uh, this pressure creates a compressive force, right, because they will be the plates will be moved closer to each other. On the other hand, because of the double layer electrical double layer, there will be repulsion between the two. So this repulsive force will try to keep this plate away. So the force will also be experienced in the opposite direction. One hand you have pressure force due to osmotic imbalance that will try to compress the plate. On the other hand, there will be electrostatic repulsion which will try to keep the plates away from each other. So these two competitive forces are acting. So we are considering this scenario, right? Right. So if this is going to be our governing equation, how we can solve this equation further? Okay. Uh, our approach is to get to the electrostatic repulsive force, right? Right. So we know what is rho star. Rho star is defined in this way. That is, we know that rho star is nothing but summation I Ni E Z, right? E into valence, electron into valence. Okay. We know Ni that we already defined in the previous lecture. That is Ni infinity exponential minus Zi E psi by kBt. This is coming from the Boltzmann distribution function. So when you incorporate this into rho star, you get this equation. This is already known to us, right? Let's say if I have to expand this equation for electrolyte, let's say 1:1. So how do we expand this? So that is exactly what we will look at. So if I expand this equation, I can expand this like, let's say Z plus. When I say Z plus, let's say we consider NaCl. You have cation and you have anion, okay, and En plus, right, and exponential minus we consider Na plus. So cation the valence is 1 plus 1. So this will be minus Z as it is, it will come, okay, E psi divided by kBt. Then you have plus. So we have Cl which is minus 1. So you can take this as minus Z, right? Okay. E n minus e power. So z is in this case will be for chlorine this will be minus z. So you will simply have plus z here. Okay. So this will be plus and this will be minus E psi divided by kBt. If you assume that there are equal number of Na and Cl, so Z plus equal to Z minus equal to Z. Okay, you can assume that. Similar way, N plus equal to N minus equal to N infinity. Okay, so in this way you can actually take out Z and N common. So in that way you will have Z E N infinity. Okay, and you will have this term that is exponential uh, you know minus z e psi by kBt. Okay, and you have minus exponential z e psi by kBt. So this is exactly what we have, and that is what we have written here also. Okay, so you can expand this equation for uh, for a case where we deal with 1:1 electrolyte, right? If you assume that we deal with 1:1 electrolyte, you can actually expand this equation from here to 3. So right, so that's how we obtain this equation number 3. Okay, so now uh, further you can substitute this equation into this rho star, right? This minus rho star. Okay, when you substitute this equation and uh, take the, because minus is already there, you will have finally this equation, that is dp. Okay, so you will have to integrate this, right? Yeah, so this you will have to integrate. Okay, so this you can integrate from infinity, so pressure infinity to pressure at the midpoint. So this one will be 0 to psi m, that is at the midpoint. Okay, so this is how you can integrate this, right? So we have just substituted the rho star into this equation, and we simply applied our integrants, right? So this is how our integral limits are going to be. Now when we integrate this equation, equation 6 will be now easily transformed into equation number 7. So when you integrate this sine hyperbolic, you get cos hyperbolic, and when you apply the limits, this will be minus 1, right? Because cos hyperbolic 0 will be 1, right? So that's why you have taken this. So that is minus 1. Okay, when you apply the limit, you will get this term. Okay. Similarly, when you apply the limit, you get delta p. That is easily understandable, right? So when you because after integration you will not have the ZE KBT term. That's why we have to remove this term here, right? Yeah. All right. So this is our equation, that is delta P equal to KBT n infinity ZE psi m square by KBT. How this is coming? Because we are applying this cos hyperbolic, we can use this Maclaurin series expansion, that is cos hy equal to 1 plus y square by 2 factorial. If we ignore this higher order term, we can simply have 1 plus y square by 2. Y here is the z e psi m by kBt. Okay. So because there is going to be 1 plus y minus 1, so 1 minus 1 will cancel out. So you will simply have y, right? And by 2 will be there. So this 2 and 2 will be cancelled with each other. So that's why you get this term. All right. So this term is clear now because we use this Maclaurin series expansion and then we obtain this. And now what we are going to do is, we have this charged plate, right? Okay. So one advantage of this, so you have one, this is psi 1, let's say, right? And this is psi 2. Okay. And when they overlap with each other, this is called midpoint. Okay, this is called midpoint. Now we know from the principle of superposition at this point, okay, the what is the potential at this point? We know psi 1, the the charge of the plate 1 is psi 1 and the surface charge of the plate is surface potential of plate 1 is psi 1 and surface potential of plate 2 is psi 2, but what is the potential at the midpoint, right? This comes from the principle of superposition theorem, that is so the psi m will be sum total of psi 1 and psi 2. So let us say you have this plate, when the electric force due to electric field acts on the other plate, okay, where this electrical double layer is nothing but the sum total of this potential acting on the plate 1 and potential acting on the plate 2 will be taken into consideration. So that comes from the principle of superposition. Okay, so that is nothing but psi 1 plus psi 2. Okay. Now if you assume that the psi 1 and psi 2, so let us say psi 1 equal to psi 2 equal to psi, then you can simply say this is nothing but 2 psi itself, right? This is 2 psi itself. So if this is 2 psi, now what we need to know is what is psi. Okay. So here in this case, the Gouy-Chapman model for larger potential was considered, because in general you can't expect always lower potential. That was due to the Debye-Huckel approximation. But if you consider the larger potential also, you can obtain this equation for psi. So if you want to know what is the psi, so psi equal to psi naught exponential minus kx was developed for a condition where there is a low potential. Okay. So that was the assumption we used. Now for larger potential, you can refer back, you can refer to the textbook authored by the Hemans and Rajagopalan, right? So there they have given the equation for larger potential, that is nothing but psi is equal to 4 kBt divided by Ze, okay, tan hyperbolic Ze psi divided by kBt, okay, exponential minus k delta. So this is the equation given for larger potential. So if you simply substitute this over here in terms of psi, in place of psi, you get the equation for larger potential at midpoint, that is psi m, that is nothing but 8 kBt by Ze tan hyperbolic Ze psi 4 kBt exponential minus k delta. Okay. So all we need to do is just we have to substitute this value here, that is psi m. So psi m was unknown. So what we determined is the psi m only. When you substitute back here, you get this equation, that is 64 kBt n infinity tan hyperbolic square Z is psi 4 kBt exponential minus k delta. This is the equation we obtain, okay, after substituting the psi m into this equation number 8. So the equation number 10 is nothing but the repulsive double layer pressure, or positive disjoining pressure due to electrical double layer. Okay. All right. So this is what we have. Okay. So this is nothing but double layer pressure, repulsive double layer pressure, okay, or positive disjoining pressure due to electrical double layer. Here in this slide, we will look at one tutorial, right? We will try to solve or we will try to get the profile between 2 nanometer and 10 nanometer separation distance, how the disjoining pressure will look like. Okay. So we are going to calculate the variation of the disjoining pressure, okay, which can also be expressed as pi subscript EDL, which represents electrical double layer. So here with the distance between two planar surfaces, so that is these surfaces are kept in aqueous NaCl solutions. The strength is given, the concentration is given, okay, and we are going to do this for two cases. One is assuming that the planar surfaces carry 50 millivolt, okay, in one case, and in another case study they carry 75 millivolt, but temperature is same in both these cases, right. So, we need to develop profile between 2 nanometer and 10 nanometer separation distance. So, basically you have to obtain the profile. Let us say your x axis will be separation distance, that will be going up to 2, 3, 4 up to 10 nanometer, okay, and we have to also develop the pi EDL, okay. Okay, this one we have developed for two case. One is 50 millivolt, the other one is 75 millivolt, okay. So, what is the pi EDL, okay, in these cases? That is exactly what we are going to develop. So, what is important is we need to develop the plot, okay, and construct the plot, okay, between x and the pi EDL for both this scenario, right. That is exactly what we are going to look at, okay, based on this equation, okay. Let us look at the equation that we have. So, we have the equation, right. So, this is function of delta, that is separation distance, okay. This we already know, this is separation distance. K is the inverse of K inverse, we already calculated, that is also given here, and the hyperbolic function. So, if you know what is Z, that is 1, valence is 1, electron constant is also known, psi is potential here, that is 50 millivolt in first case, okay, and then we need to calculate. So, N infinity is the bulk concentration. So, you need to multiply the molarity with respect to Avogadro number, so that you will get number of ion per meter cube, okay. Since the problem is given in moles per meter cube, we do not need to multiply with 1000, right, and KBT is given, KB value is known, temperature value is known. So, all we need to do is just plot between 50 millivolt. In first case we have to plot 50 millivolt, that is 0.05. In second case the variable will be 75 millivolt, that is 0.075, okay. In both the case we have to change this separation distance from 2 to 10 nanometer, okay. So, this is how the plot look like, okay. The orange line represents the disjoining pressure as a function of distance for 75 millivolt, okay, and the blue line corresponds to 50 millivolt, alright. So, you can do this exercise by yourself using MATLAB or Excel, so that you can understand the concepts behind this disjoining threshold, right, and how to calculate the disjoining pressure between two planar surface when the electrical double layer overlap, okay, at a different separation distance, okay. We will stop here, we will continue from the next lecture. Thank you.